Today we're going to be talking about flight. We've already addressed some of the adaptations that birds have that give them the ability to fly, but we're going to hone in on their wings and I'll get a little bit into physics about how they allow flight. Now, don't get too overwhelmed by this. I'm not going to ask you to calculate any formulas. We're not going to dig in that deep, but I do want to examine flight to get a better sense of how the physics of flight influence the lives and behavior of birds based on the size and shape of their wings. So I think this is going to have actually implications for just looking at different types of birds and say, why does this bird fly like that? And why does that bird fly like this? So I'm going to share my screen here and we will get this thing started. And let me flip this again. Okay, again, we are quite aware of the remarkability ability of birds to fly, but what is it about their wings that lets them be so successful at that? Well, if we visit the world of the physics of aerodynamics, imagine if you have ever been on an airplane. I imagine many of you have, most of you, perhaps all of you. If you're sitting next to the wing and you look out, this is kind of the shape you see. And this shape is called an airfoil, where it's thick at the front and then it's thin and tapered at the tailing end and has a slight down curve. That's the shape of airplane wings, and that shape is also the shape of bird wings. Now, this is not the shape of a wing looking at it as if, you know, this was a top-down view. This is as if you're looking out from your window out towards the airplane. So to the left is the front of the airplane, to the right is the rear of the airplane. And in this case, to the left is the front of the bird and to the right is the rear of the bird. So we've seen this shape all over the place. Almost everything that can fly has this shape. So bird wings have roughly this shape, and insect wings and bat wings and pterodactyl wings and airplane wings, they all use this, and helicopter blades, they all use the same rough shape. And there are four different forces that are acting on this wing. So in order for a bird to fly, it has to have lift. That's what is going to pull it off the ground. And then we're quite familiar with what is counteracting that, which is gravity. In order for a bird to fly forward, it has to have thrust. Airplanes use engines to create thrust. We'll figure out how birds accomplish that in a different way. And then drag is what's counteracting thrust, which is what's slowing them down, which birds sometimes intentionally create. So, you know, they want to slow down too. So we'll visit a little bit of elementary aerodynamics to look at how this works. So what are the sources of these forces aside from gravity? Gravity is different, right? So let's talk first about lift, because that's the most remarkable thing. Lift is produced by the forward movement of this shape, this airfoil shape, into an airstream. So this can happen in two ways. It can happen, you know, by a bird creating thrust and moving quickly through the air, or it can happen, as we've all seen, by a stationary bird in a very windy environment. So either you can have wind, air passing over it just by being in a windy place, or you can have air passing over it by moving forward. And if you move forward, or if you have great wind with this shape, then you are going to get lift. And it's generated kind of in two different ways. We can't isolate it as just one or just the other. It's a combination of two. And so one is the Newton's third law of motion, and one is something called Bernoulli's principle. Okay, so Newton's third law of motion says that for every action, there's an equal and opposite reaction. And so if we imagine that that shape, the shape of the airfoil, we'll just back up here. When the air is going over this wing, the air that hits the bottom side of the wing is going to push up because of how that wing is slightly downturned. It's going to hit the bottom of that wing, and it's going to force that wing up. That's that equal and opposite reaction. So the wind hits the bottom of the wing, and the equal and opposite reaction is for the wing to lift up. And so that's how Newton's third law of motion, when the air is flowing over the wing and under the wing, the air that flows under the wing hits the bottom of the wing and pushes it up. The second part is Bernoulli's principle, which is more actually about air flowing both over and under the wing. And so Bernoulli's principle says that whenever you increase the speed of a a gas or a liquid, it will result in a decrease in pressure. Okay, so an increase in speed means a decrease in pressure. And so if you, because of, again, the shape of this airfoil structure, when the air moves over it, it causes an increase in speed. The air speeds up just slightly as it is pushed over the wing. And what that means is you get a decrease in pressure, and that wing is just going to go naturally from low pressure to high pressure, or sorry, high pressure to low pressure. So you're going to actually create lift by having low pressure above the wing. Okay, so that lift then, the airfoil shape produces a positive lift to drag ratio, and it allows you to fly. Okay, so if humans had this same airfoil shape, we could also fly. And obviously we sort of accomplish that in a number of different ways with gliders and with you know, different contraptions that humans have tried to invent, mostly unsuccessfully. But this does work. And there's a video that I'm going to have you watch that will help you make sense out of this. Okay, now what about the thrust? How does the bird get forward movement? Thrust is accomplished, again, in airplanes by having a propeller or a jet engine which forces the wing forward. By forcing the wing forward, you get that you know, air hitting the bottom of the wing and forcing it up, and the air speeding up over the top of the wing and causing it to slow down. Oh, actually, you know what? Before we even move on, I'm going to switch really quickly here. Back to me to show you an example of Bernoulli's principle. So you can all do this if you have a sheet of paper laying around. Grab a sheet of paper and put it in front of your mouth and then blow as hard as you can over top of it, and you're going to see something happen. Watch this. You see that? When I increase the airspeed, it decreased the pressure and created lift. Here's Bernoulli's principle for you. Okay, so exciting. Okay, here we go. So airplane, again, produces thrust by its propellers or engines. Birds produce thrust by flapping its wings. Now, the tricky thing is if it just flapped its wings parallel like this, it wouldn't work. It accomplishes this by rotating its wings. When it flaps forward, it actually rotates its wings so that the angle is slightly forward. And so we're going to watch a video that's going to help us understand all this stuff. Okay, so now we have a little bit better sense of thrust and lift, which are the things that allow birds to fly and to move forward, create powered flight. We also need to understand drag. Drag is what is counteracting thrust. And so basically drag decreases speed. When you counteract the thrust, you decrease the speed. And when you decrease the speed, you decrease the lift, right? So drag not only slows the bird down, but it also makes it more difficult to fly. Now, what's interesting about this is that the drag can be manipulated by the bird by the angle that they hold their wing. If they hold it quite upright, as you can imagine, there's a lot of drag. And when it's held relatively flat, you get relatively little drag. So birds are quite experts at manipulating lift, drag, and thrust so that they can fly at just the right speed and just the right angle and just the right direction to meet their needs, okay? And we can see that that they will manipulate drag in one obvious place that is that whenever a bird needs to come in for a landing, right? They are going to take their wings and hold them at a certain angle to create as much drag as possible. And in this little eagle GIF, we see that that it is got its wings almost perpendicular to the ground, and that's going to create a lot of drag. We also see usually that when birds come in for a landing, they usually come up, right? So they sort of slow down and they just land just right on time. So birds manipulate lift, drag, and thrust to meet their needs. Now let's take these ideas and apply them to bird wing sizes and shapes. Here we have a wing on the left of maybe a falcon or a shorebird, and a wing on the right that could be like an eagle or a heron or a crane or something like that. Which one of these wing shapes, one with the primary feathers all very visible and sort of individually exposed to the air, and one with the primary feathers all tucked in so it's very much more streamlined, which one of these would create more drag? What do you think? So ponder that for just a moment. Yeah, the one that has the feathers exposed is going to create more drag because every single one of those feathers is going to create its own drag. And we'll also find that broader wings are going to create a little bit more drag, but a little bit more lift, right? So the bird flies more easily, but it does so at a slower pace. And so we're going to start to see how this will explain the different patterns of flight in different birds. Okay, so how do wing size and shape influence these forces? Well, we take all of this together and put it together in one little package that we call aspect ratio. And the aspect ratio is saying how long is a bird's wing and how wide is a bird's wing. And so if you have wings that are long and narrow, we say that those are high aspect ratio wings, so that the ratio of length to width is a big difference, right? So high lift to drag ratio, that means the leading edge of the wing is responsible for most of the Bernoulli induced lift, and you get very good flight. So they can fly at high speeds with relatively little effort. They have so what the best example of this bird we see in this picture is an albatross, which is an ocean bird or a pelagic bird. And I'm going to show you this little video, or I'll at least give you access to this link of an albatross flying over the ocean, high speed and low input, low power, meaning that they aren't flapping their wings. But this also means that they are not very maneuverable, as you can perhaps imagine. This is not made for good tight corners and angles, but out in the ocean, you don't have to worry about running into branches or anything. So it's okay that they aren't really good at their tight angles and corners. So I'm going to show you a different little video here of an albatross flying. Okay, from that video then, we can see that the shape of a bird's wings is highly indicative of their behavior, their flight style. So those albatross with those very long, very narrow wings are made for very low effort to fly. They have very high lift, so they can fly without having to flap. But it also means that they are not going to be very maneuverable. While they can sort of soar and bank, they don't live in an environment where they're going to have to make tight turns. So without those ideas, then we can then look at these different styles of wings and predict what the lifestyle or the niche of the bird with these wings is like. So we've got long, narrow wings in style A. We've got fairly short, broad wings in style B. We've got sort of short, narrow wings in style C, and we've got fairly long and broad wings in style D, right? So how do these wing shapes influence the style of flight and therefore the niche? The niche is sort of the method by which this animal lives, right? So your niche is either, is it soaring, or is it powered flight? Is it migration? Is it living in the forest? All these sorts of things, right? So let's look at these. So style A, the one that we just saw on the albatross, we call that the high aspect ratio. Long, narrow wings, really fantastic for soaring at high speeds, and out on the ocean, those high wind speeds create sort of artificial high speed. They're not actually flying that fast, but because the wind is flowing over their wings so quickly, it's effectively fast. And that's a style of wings that is very well suited for birds that live in the ocean. Okay, so high aspect ratio, that sort of albatross. There are many other ocean birds, we call them pelagic birds, that have that high aspect ratio style wing. Style B, we call an elliptical wing. And this is short and broad. And this is a style wing that you would see in little small songbirds and maybe some more medium-sized birds, like game birds like grouse and turkeys and quail and those sorts of things. And they are going to be good. Number one, being short means they're more maneuverable. Being broad means they're going to have fairly high drag, meaning that they are not going to be super fast flyers unless they flap really hard. But because they're short, they're going to be maneuverable. Okay, so these elliptical style wings that are short and broad, they are going to be great for living in a forest. Extremely maneuverable because of the shape of the feathers, the way the feathers are fanned out, because they're not pointed, when they flap their wings, they get a lot of lift. And again, if you watch these little small songbirds maneuver through the forest, you see they aren't flapping very hard just to get off the ground. So really high lift, and not very high speed unless they flap really hard, but really maneuverable because they're nice and short. And so they're suited to living in a forest or shrubby environment where maneuverability is really important. Style C is a high speed style, sort of like the high aspect ratio style, except it's a shorter length. So it's high speed, but it requires more flapping. And this is a style wing that we see in falcons, shorebirds, and hummingbirds, and swallows and swifts. I'm actually going to play another little video for you here that shows us the story of the fastest bird in the world, which is the peregrine falcon. Actually, I think I already have that pulled up. Let me, so they, again, with the pointed wings, they're going to have low drag, which means high speed, but because the wings are narrower, they're not going to get as much lift, which means more flapping. And if you want to dig into peregrine falcons and how cool they are, there's all kinds of cool stuff out there on the internet. We actually now know that they can fly as fast as 200 miles an hour. But again, it's not with flapping flight. It's, as we saw in that video, by getting up high up in the sky and then folding their wings in what's called a stoop, and then coming down a very high speed, basically just with gravity, and then pumping their wings a little bit to make it even faster still. And so that wing shape is great for very high speed. All right, and then wing shape D is called the high lift wing. So it's longer like A, but it's much broader. It's not pointed at the tips. Each primary feather is exposed to the wind. And so this is made for very high lift, but slow speeds. So this is not for fast flight. Not unless some of these birds with these type of wing can fly fast, but it's like the peregrine, when they tuck their wings in, then they can fly quickly. That's mostly true for birds of prey. But for things like hawks and eagles and herons and cranes, they are not speedy flyers. They're not super fast, but they get an advantage in that when they put those wings out, they get very high lift, and a couple of flaps gives them enough lift to get off the ground. And so they can carry heavy loads. They can soar at very low speeds with very little energy input. Once they get a couple of flaps in and get their bodies off the ground, they often just soar with their wings outstretched without having to flap them, right? So advantage, low energy input. The disadvantage, low speed. So they can't use speed as their strategy for hunting unless they pull their wings in. And we will see some of those birds of prey that have not the falcon-like wings like style C, but the hawk wings like style D, that'll pull their wings in and they still get an advantage of some speed. Okay, so really cool. This is fun to see these different, this is basically the 4 different styles of wings. And now you'll get a better sense when you're out in the field, identifying birds and watching them and enjoying their behavior, how their wing size and shape and the way they hold their feathers, whether they're pointed or spread out, very much influences the style of flight that they use. And let's end with this most remarkable of flyer, which are the hummingbirds, and they come in different sizes and shapes, but hummingbirds beat their wings between 12 and 80 times a second, not a minute, a second. So they're beating their wings very, very fast. And as you probably know, have the capacity to hover. Not only can they hover, they can fly backwards, they can fly sideways. So based on what you know, or maybe even have seen, think about how a hummingbird is able to hover in place with flapping wings. Okay, these are a couple of YouTube videos that will take you to some slow motion video of hummingbird flight. I'll let you watch those on your own, but it's something fun for you to ponder as we consider the amazing ability of birds to fly and the physics that are required for it to happen. All right, I hope that was helpful and interesting. Let me know if you have questions, and I'll be happy to get them answered. This is the end of the material. Thanks.